now our next talk is surprise, surprise. It was meant to be the third talk in the session. So thank you for the availability. So yeah, it's my pleasure to introduce Angela Robinson from NIST and FAE graduate. Very proud to have Angela here to talk to us about some investigation about bike and errors in QCM codes.
Thank you. So yes, the title changed slightly. This talk is definitely related to the bike decoding failure rate, but we reframed sort of the title as a study of error floor behavior in QCM DPC codes. So this is a joint work with Sarah Arpin, Tyler Billingsley, Daniel Haas, June Lau, Ray Perlner, and myself. Okay, so the motivation bike is a QCM DPC code-based algorithm. This is one of the alternates in the NIST third round standardization process and one of the 3 code-based algorithms still under consideration. So we've already heard today talks related to classic McAleese and HQC. Bike in the round 3 specification made the formal NCCA security claim. And so it's important to, although bike was designed for CPA security or ephemeral use, there's a static key version, and the GJS key recovery attack exploits decoding failures in an NCCA security model. So it's important to assess the decoding failure rate of bike to ensure that the rate is low enough to prevent this key recovery attack. So what is an error floor? The graphs of decoding failure rates, typically on a log scale, for low to moderate density parity check codes with iterative decoders display this phenomenon known as an error floor. So initially, the probability of decoding failure dramatically reduces as the signal to noise ratio increases, and then there's an eventual plateau. It becomes more of a linear decline. So the initial rapid decrease is referred to as the waterfall region, and the eventual plateau or more linear decrease is known as the error floor region. This is just an example of error rate graph where you can see there's clearly sort of like a concave region and then more of a linear region. So why is this important? Because the decoding failure rate for bike is essential to achieving CCA security, it's important to have more confidence in what the probability of decoding failure is. Unfortunately, a direct computation of the average decoding failure rate for a cryptographically relevant security level is infeasible by design. So the approach several works have taken is to compute average DFR directly for smaller security levels and then use extrapolation techniques to approximate to larger block sizes. And a lot of this work was within the scope of determining what is the best decoder to use. So bike has, in its current version, is using the black-gray flip decoder, and that was based on a lot of the results cited below, determining what is the best decoder, and as well as the number of iterations to ensure a constant time algorithm. So although the extrapolation is very helpful, in order to accurately predict the DFR, in order to avoid underestimating the DFR, one must properly understand the error floor behavior of the decoding failure curve. So for LDPC codes, there's plenty of, lot of results in the literature. Typically, the approach is to represent the code in a Tanner graph form. It's just an equivalent representation of the code. It's a bipartite graph. It's very sparse in the LDPC case. And there are results on the minimum distance based on the length of the shortest cycle in a Tanner graph. There's also results that note that the prevalence of small closed loops within the Tanner graph increase decoding failure probability. So here's a definition that comes from McKay and Postel and is used throughout the literature. for some parity check matrix describing a code C, a UV near code word is an error vector of weight U whose syndrome has weight V. So it's simply just a way to classify error vectors involved in syndrome decoding. And it was determined that when near code words have a small u and a small v, so a small weight and syndrome with small weight, these near code words cause high error floor for certain LDPC codes. For the MDPC codes, the Tanner graph is less sparse, right? And so it's sort of assessed that it's too expensive to extend these Tanner graph techniques directly to the MDPC codes. However, near code words and low weight code words may still be main contributors to the error floor region. And in 2019, Valentin Vasseurs' thesis defines 3 such sets and analyze their impact on the bike decoding failure rate. So I'll describe these sets shortly. So bike at a high level, a very high level, bike is based on binary linear code. So we'll be discussing everything over GF2. Bike is designed with a quasi-cyclic structure. So the private key is composed of circular blocks. In the case of bike, in its current state, just 2 blocks. So the private key is 2 circular blocks, H0 and H1. And these are moderately dense parity check matrices. So the row weights are on the order of square root of the dimension of the code. Sorry, the length of the code. So let R denote the circulant block length and T the max error weight. Then the secret key is a parity check matrix of size R by 2R. And the public key is just a secret key in systematic form. A message would be encoded as an error vector of weight T of length 2R, and the ciphertext would be more or less the syndrome of length R. And again, you would decrypt using the black gray flip syndrome decoder, which is an iterative bit flipping decoder. So at a high level, the parameters are the block length like that I mentioned, the row weight of the secret key, the maximum error rate, and the security parameter. And we used Bike's design principles, so I need to mention them here. R must be prime, X to R minus 1 should have only 2 irreducible factors modulo 2 to prevent further decomposition, and also to ensure that this secret key can indeed be placed in systematic form. The row weight is on the order of square root, in this case 2R, and the row weight is also even, but the row weight divided by 2 is odd. And based on the information set decoding, which is the best known algorithms to break the syndrome decoding problem, this approximation at the bottom is used to sort of guide the relationship between the bike parameters. So our approach to better understand the error floor behavior of bike DFR curves, we consider a scaled down version of bike. So we focused on a 20-bit security level for the sake of being able to run, say, exhaustive experiments. And we used the bike design principles to generate parameter sets at the 20-bit security level. Because fortunately, these decoding processes are highly parallelizable, we use the Boston University shared computing cluster to run our experiments. And we examine factors that increase decoding failures affecting the error floor. So here we were able to visually see where the error floor occurs for security level 20, and I'll go into more detail about this. So I already mentioned the parameter selection based on the design principles. We initially started at block size 523 with row weight 30, error weight 18 for the 20-bit security level. And then in order to achieve this graph, we sort of had to extend block sizes to the left and to the right to locate the error floor. So we we gathered more block sizes, which will be shown later. Also, a part of our method was to consider weak keys. Valentin classified 3 sets of weak keys for bike, and we essentially filtered out these weak keys to avoid inadvertently affecting the DFR. In bike's case, there is a threshold associated with determining when a key is weak of type 1, 2, or 3. The threshold for bike at the cryptographically relevant security levels is 10. Based on our experiments, we had to reduce the threshold to 3. And how we computed the average GFR was pretty much fix the block size R. T is 18 for all intensive, all error weight is 18. So we would sample a random key, reject it if it's weak, sample a random message of weight 18, compute the syndrome, run the black-gray flip decoder on this pair, HS. And if the output doesn't satisfy the fact that H times the output transpose matches S, or if the output is not equal to E, we consider it a failure. And we repeat in times where N went as large as 100 million. So, and then we saved the failures. When there was a failure, we saved the error vectors to study them. So because the set of weak keys is far more dense for small r, it was very time consuming to run this experiment for smaller block sizes. So you'll see that these lower below 500-ish have fewer trials. And also the decoding failure rate was so high, it's kind of pointless. Then for the higher block sizes, decoding failures were harder to find. So it took 10 million times just to find 2 or 3 decoding failures. And the error floor begins somewhere around here. So we tried to concentrate our efforts and run more simulations for the beginning of the error floor. Also, all of our raw data is available on GitHub. So how much time for?
7 minutes.
7? Okay. All right. So besides the weak keys, then Bassour's thesis also identified these special sets of error vectors. So recall that low weight code words and near code words, UV near code words, are expected to cause decoding failures. So based on the structure of bike, Bassour was able to identify two sets initially. So the low weight code words can be constructed based on just the code. So if you have the secret key, it's a representation of the code, and you rewrite it in terms of the generator matrix, and the rows are code words of weight W. So these are low weight code words, call this set C. So that's the first set. Then the near code words, right? You're looking for a set of vectors with small weight whose syndrome also has small weight. And because of the quasi-cyclic structure of the key, there's this result, which if you worked it out, might be obvious to you, but it was very helpful in identifying a set of near code words. So these circulant matrices, first of all, the ring of circulant matrices of size R by R is isomorphic to the ring of polynomials over x to r minus 1. So you can either think of the key in terms of matrices, you can think of the key in terms of polynomials. If you think of it in terms of polynomial and rewrite a cyclic matrix in its polynomial form, the support of that polynomial is preserved when you square it. So here, this is helpful in identifying that if you simply just take one of the 2 blocks of the key and the error vector matches one of the blocks and zero out all the others, the weight of the error vector will be preserved. It will match the weight of the syndrome. And so this is essentially the first class. Say you take the first half. So vectors of the form where the first half, the first R bits match, say, one of the rows in the first block and zeros in all the other positions. These have weight D, W over 2, and the syndrome also has weight D. And you can do the same thing for the second half. So this was the second special set called the set N. He calls the set N. And this is just the union of these two vectors of this form, including all of the rows. So this is a DD near code word. So you have the C set, the N set, and then the third set, he just takes as sums of two vectors in N, in which case there is a slight possibility of cancellation, or there's a slight possibility of increasing the weight just by summing the two different vectors. But overall, the third set still has the low weight vectors with low weight syndrome. So what we did is we examined the recorded decoding failures that we saved at R equals 587, 613, and 619 to see how close are our failure vectors to these three special sets. And closeness is captured by the variable L. It's just the size of the intersection of the set bits between the error vectors, well, really between any two vectors, but we're really looking at the vectors that we saved from our experiments that cause decoding failure to see how much of an overlap is there in the set bits of vectors in the special sets C, N, and 2N. So here's the initial graph. The largest overlap, the most frequent overlap was 3, intersection of size 3 and maximum of 10. And we compared this to just a randomly sampled vector. So we compared the proximity of failure vectors to these special sets with randomly generated vectors of weight 18. And it turns out that the size of the intersection isn't so different. So any randomly generated vector, also there's a high frequency of overlap with the low weight code words and the vectors in set N. So it seems at face value, also the results are consistent for block size 613 and 619. This is 613 and 619 looks very, very similar. It doesn't appear that there's a difference. So we hypothesized that maybe it's just syndrome weight. Maybe these sets aren't the leading cause or the leading factor in identifying decoding failures. So we compared all of the vectors that caused decoding failures from our experiment, and we looked at their syndrome weights and compared them to just randomly selected vectors, computed their syndromes, computed the syndrome weight. And it looks like the vectors involved in decoding failure do have lower syndrome weight, but is the difference statistically significant? So we went through to determine the significance. The null hypothesis would be there is no difference between the syndrome weights, and the alternative hypothesis would be that randomly generated vectors induce syndrome weights higher than those involved in decoding failures. And the result is that for significance value 0.01, block sizes between 509 and 619 do have a statistical significance that the syndrome weight is smaller. At 653, the p-value is not below, so we can't reject the null hypothesis. But also at 653, there were only 5 decoding failures. So we determined that from 509 to 619, vectors involved in decoding failures did have lower syndrome weights overall. So this is ongoing work. Of course, it'd be ideal to identify another class of near code words or another class of low weight code words. And also there's the question of whether any of the Tanner graph approaches do apply. The computation involved in computing the girth of a tannograph isn't parallelizable, so we weren't able to harness the computing power of the shared computing cluster to attempt that. So have to acknowledge Valentine and Paolo Santini for helpful initial code, helping us with the black gray flip decoder and also answering questions. This collaboration was initiated through the Rethinking Number Theory 2 workshop, and there was also support from the Simons Foundation. So thank you.
Thanks, Angela. You're perfectly on time. So,
Okay.
now we have
you mentioned there are 3 classes of weak keys that you reject. Could you just say something about what makes them weak?
Yeah, so the first class is, and again, this is not our work, this is Valentine's work. The first class is keys that have a large number of consecutive ones in a block. This was something that we, in a different paper related to lead decrypt, can cause problems. So if a lot of the ones are grouped together consecutively, that's one. And also he looked at intersections between columns of one block of the key, that's 2. And then the third type was intersections between columns in the first block and the second block. And it was influenced by the GJS attack paper based on like the distance spectrum of your rows. You looking at how far apart are the set bits and if there are multiplicities there. So it's related to like this multiplicities of evenly spaced ones in the keys. Also from our experiments, we seem to agree that those are pretty much the extent of the weak keys. We didn't see any other issue beyond those.
So if you get a weak key, what kind, then the GDS works, or what do you break? Do you break CCA encryption?
I think, well, for sure, the weak keys increase the decoding failure probability. So I imagine that it is related in the end to the GJS attack, which would break CCA security because it only applies to the CCA settings. So yeah.
Error floors are usually a manifestation for LWC codes, turbo codes, but amazingly, polar codes don't have that effect of or suffer that much of error floors. Is anybody considering actually to replace some of these codes with polar codes?
Eduardo.
we have not looked too much into this, but I am aware of some previous work on components.
There are also floors there or not? Because in the literature so far, I couldn't see that much floors about polar.
But do they have, can you model the DFR in like a closed form for the polar code? Because like HQC has a closed form analysis of the DFR, so you don't even need to look at the DFR curve.
No. I guess the point of the matter is exactly, I think, should be evident from this talk and the previous talk. You see that as soon as you have the coding failures, then it gives rise to all sorts of carbon attacks, and we cannot estimate. You're not sure what happens to the whole point of what is happening with NIST and the fact that these two solutions with non-trivial coding rate are still in the realm of like, okay, that's the whereas the classic mechanism and algebraic decoders with zero rate. That's a big difference. And I guess We actually have a question from the YouTube, so I will read it, and it's more an observation, but it's an observation from Marco Baldi, and he's mentioning that we presented at City Crypto last year, and they derived some bounds showing that the DFR decay is always polynomial in the code length asymptotically, and so basically this confirms that the error flow always exists.
Yeah. Oh, okay.
So
Yeah.
I don't know if you want to comment on that. But.
Yeah, and also one thing that I found similar in the literature about the error floors, it seemed like all of the codes involved were regular codes, and like every row has the same weight, every column has the same weight, and I'm wondering if maybe this is, I'm not sure like the extent of it, but it seems like regular codes with some sort of iterative decoder, this will appear. So, I don't know. But thank you. Yeah, I'll talk to you, Marco.
But yes, so definitely, I think we should thank Angela again for the very interesting.